I'm going to show you guys a graph. And I want you to guess what a good equation for this graph would be. Do you guys see the graph? What kind of a graph is that, do you think? Yeah, so a good estimate would be y equals x, right? It's not y equals x. It is. Okay, I really want you guys. You ready? Okay. Do you guys see that? Y equals x is here. I'll even take that away. I'm gonna graph that on top of this one. That is the equation that gave us this graph. And the reason it looks like a line right now is, do you guys see how zoomed out I am? So I let x get pretty big, didn't I? So this is the third type of asymptote. We have a vertical asymptote, we have a horizontal asymptote, and if I take a horizontal asymptote and I just poke it a bit, it becomes a slant asymptote. So watch what happens when I zoom in. So it's not a straight line, especially when x is small. But when x gets big, for some reason that makes it become linear. In fact, if I graph y equals x on top of this thing, in the middle is nowhere near close. Right? Well, it's not crazy far, but it's like not this. It's definitely not the same thing. But if I zoom out very quickly, holy shit, this thing goes crazy. Very quickly, it matches the green line. Yes? Okay, that's exactly what a horizontal asymptote does. Yes? It can do weird shit in the middle, but horizontal asymptote says at the end you better start to become me. You better start to approach this. So can you guys please? Can everybody see this equation here? I'll write it down. Can you guys see that equation? Here, I'll write it down. Because what I want you to do is I want you to divide that. So here, I want you to divide this. Can you use synthetic division? Let me say this a different way. You could, if you wanted to divide synthetically by two complex numbers. Why can you not use synthetic division directly on this? Because the bottom is not. No. It's not x to the 1. It's not linear, right? When's the only time synthetic directly works? If the bottom is x plus or minus a number, yes? Me, being an asshole, made the bottom x squared plus 4. So how do you divide that? Long division. Okay, go. I'll wait. Do it. Do that. Bless you. I want to get paid just to sit here. I love it. I'm joking. Just do that problem. Got to keep long division alive because synthetic doesn't always work. Double check that I put. I didn't. See if our assumption was correct that it's y equals x. How does long division work again? What do I do? X. Yeah, x squared times what is x cubed? X times x squared is x cubed. Now be careful now, watch this. X times 4 is 4x, and I put 4x over here. You guys with me? So then minus x minus 4x is
Negative 3x.
bring down the minus 1. X squared times what is 4x squared? 4. 4 times x squared is 4x squared. Why did I put a 0 there? 4 times 4 is 16. Change the signs. Line up your like terms, right? So I get minus, well, I'm gonna just go write it like this, so it's not too weird. Okay. That's what you get. Now, real quick, somebody remind me, where do horizontal asymptotes come from? Letting what happen? No. So there's 3 situations. One was if the degrees are the same, then it's the ratio of the coefficients. The other one was if the bottom degree is higher, then it's 0. This is the third one. But where do they come from? They come from letting x get really big. What happens to this piece if I let x get really big? Where's the degree higher? On the bottom. The bottom is growing faster than the top. So as I let x get bigger and bigger, that's going to get, if I divide by bigger, I'm getting, if I divide by bigger numbers, I'm getting smaller outputs, yes? So this is going to go to 0. So then the actual equation of the line is x plus 4. So we were pretty close. So let's go back. So here's how slant asymptotes work. How do I know when there's a slant asymptote? Well, if the top power is smaller than the bottom, y equals 0. If they're equal, y equals a ratio of the coefficients. So what's the only other situation we have if the top power is bigger? So anytime the top power is bigger than the bottom power, you're going to get a slant asymptote. So if we go back, if I adjust this just a little bit, it'll fit even better. Now look at that. It only doesn't fit down here, yes? So just visually, y equals x is pretty close. But if I long divide, I can get exactly what line this has to follow. Does it make sense that the top degree is higher, the top is growing faster? If the top grows faster, the bottom can't keep up. I'm gonna overall get bigger and bigger and bigger. I'm gonna go to infinity. But I'm gonna go to infinity following that green line. So my asymptote just slants, right? Or this way. So that's, math people being creative. We said, oh, it's an asymptote slant, we call it slant asymptote. So we call it slant asymptote. The other name is an oblique asymptote. So if you work out a lot, you'll appreciate that. You work on your obliques, yes? Slant to me makes more sense. How are we feeling? So why did this come out to be a linear asymptote? Do you see it? That's a line. Yes, that green is the line. Why did it come out to be linear? What was the degrees on the top and bottom? The top is a third degree, the bottom is a squared. So effectively, if I cancel 2 x's out, I'm going to be left with x something. That's why we got x plus 4. So what if the bottom was, I took the square away? What if I took the square away? I really want you guys with me. What if I took the square away and made the bottom just x plus 4? What's the highest power that should be left when I do division? If I have an x cubed stuff divided by x stuff, what should be the power left? X squared, yes? I'm going to lose 1x instead of 2. So what should the slant asymptote be then? It'll actually be parabolic. So watch this trippy shit. If I just take the squared out, let me take this away. If I go out now, look at this weird thing. You ready? If I go out far enough, well, let's see if I can do this. Hold on, I have to directly control this thing. Crap, I need glasses. Drawing much. All right, no x. Don't go that crazy x. Let's go Let me do stuff. There we go. Okay, that's better. There we go. Do you guys see if you ignore the middle, it looks like a parabola? Yes? So that's why horizontal asymptotes are related to end behavior. But now when if I long divided x into x cubed, of course I'm going to be left with like x squared plus other shit, yes? So of course I should expect it to look parabolic when x gets big. In the middle, what's it look like? Weird shit. In fact, what's right here? There's a vertical asymptote at, you can do it. Where's the vertical asymptote? -4. Yes? And if I zoom out a bit more, then it really looks parabolic, yes?
Yeah.
If you ignore that middle red line, it looks just like a parabola. Okay. Stay with me now. All right. If the top power is higher, the bottom can't keep up. The numbers are just going to keep getting bigger and bigger. I'm dividing by something that doesn't keep up. So of course my outputs get bigger and bigger, but they get bigger in a prescribed way. They have to follow that problem. In fact, can you do it, Jeff? X squared. Well, it should be x squared plus. No, it'll be messed up. It should be almost this. Let me see if I can guess what it's going to be. Yeah, it's almost that. Yeah, I don't want to long divide this thing, but if you long divide the thing, you can see what the parabola should be. That is following. Okay. All right, is everybody kind of with me? So unfortunately, now real quick, I'm being silly because what could I use on this to divide it? Synthetic. I forgot I changed it. So if the bottom is just x plus 4, so x plus or minus something, synthetic that damn thing. Will you have some that? Yeah, hell yeah. You'll have some that you can't use synthetic. Too bad. So you got to remember your long division. Okay. So that's one idea that I did forget to go over because I'm teaching the exact same stuff in my other class, and I just sometimes I don't remember which class I didn't talk about it. Anything else from homework stuff? Okay. So let's do this. Last time we got into exponentials. And I want to continue that discussion today. We drew an inverse function. So let's do what we did last time. Let's recover what we did last time. What was the example I gave you guys to get things started? You guys remember? What was the example at the beginning of the discussion? I was giving you something I don't have much of. But in the pretend situation, I was giving you a lot of it. Yes, I was giving you $1 million, or I'll give you 1 penny, and then tomorrow I'll give you 2 pennies, and then the next day I'll give you double that, 4 pennies, right? I said, which one would you want to do? Most people would say $1 million if they've never heard of this. But the doubling, if you double or triple, it will increase stupid fast. I mean, dumb fast. So what we discovered is, if you get the pennies and double it every day for 30 days, you will get about $10 million roughly, versus 1 million right away. Are you guys all with me? Okay. So this is what's called exponential growth. And we call a function that captures exponential growth. You're never going to believe this. We call it an exponential function. And I think I told you guys before that the way I used to always introduce this was the whole idea of we've shoved x in the denominator, we've shoved x into powers, not in the powers, but like x squared, x cubed. We've shoved x in the roots. Where have we not shoved x yet? In the actual power, right? So we have to know what these kind of look like, how they act. So the very first thing was we graph this thing. Can anyone remember doing the air what an exponential function looks like? Kick ass, right? It looks like that. Yes? Looks like somebody taking off. Ha! What aspect of it reminds us of chapter 5? What's happening? So over here, if I let's specifically do 3 to the x. What do I get when I plug a 1 in? 3. And of course, when I plug a 0 into anything that looks like this, except the beta 0, I get 1. And if I plug a negative 1 in, I get 1 over 3. So it looks like this going this way, that's the explosive growth. That goes up faster than x to any power. X to the billionth power, 3 to the x will eventually go up faster. X to the billionth power will start ahead of it, but 3 to the x will catch up because it goes up so fast. Is that all with me? We saw that with the pennies idea. You start with 1 penny on the first day and you get up to like $5 million on the last day. Holy shit, 30 days later. What's happening back here?
It's getting small.
Yeah, 3 to the negative x is 1 over 3 to the x. So when I throw negative numbers in, it's going to be 1 over something. 1 over 27, 1 over 81, 1 over blah. I mean, so it just keeps getting smaller, but it never gets to 0. So of course that's the idea of an asymptote. 11, in this case horizontal. Kick ass. So somebody asked a earlier question earlier, they said, can asymptotes only come from these ratios of polynomials, these rational functions? No, this is one place where we have an asymptote that just happens naturally, it just approaches that thing. Stop for a minute. Is everybody still with me? So how would I graph this then? How many transformations are there? 2. What are they?
X minus 1 and
Yes, so be more specific. That's where they come from. What are the transformations?
down 1? No.
What's the negative 1 with?
Yeah.
What variable is the negative 1 with? And which direction is x control?
So,
X controls left and right, so that's going to go right 1, and then down 2. Kick ass. I need you to understand what's happening right now. We got a brand new function, just out of nowhere. We've never done transformations of this something. The idea of transformations does not care what function you're working with. It works with every function in the exact same way. That kicks remarkable amounts of ass. So if I put x minus 1 wherever the x was, I don't care what the function is, it's gonna go right 1. What the function? And if I put a minus 2 after it, it's going to go down 2. So now I could do just like we did before. I could take a point, I can go right 1, and I could go down 2. Take a point, and go down 2. And what? Go right 1. Now, got to be a little careful here. Go right 1, and then down 1, 2. Can anyone tell me where the asymptote goes? Yeah, what is the asymptote? It's like an infinitely long dotted line, correct? In this case, it's horizontal. So if I move it left and right, does it actually look different? No, it's infinitely long. You can move it this way 1 billion times, it looks exactly the same. So the only thing that's going to make it move is up and down. So it was at y equals 0, so now it's going to be at y equals negative 2. Everything goes down 2. So whenever you do transformations to an exponential function, you have to indicate where the asymptote ended up. Okay, I like it. So what's really great about that is you learn transformations once. They never change. You interpret them exactly the same no matter what the function is that you're looking at. What did we do immediately after we graphed an example exponential function? We did something. Let me graph another one. You guys help me out. How would I graph 2 to the x? Can somebody give me the 3 main points here?
0, 1.
0, 1, good. 1, 2. What do you get when you put a negative 1 in? 1/2, good. So don't forget, negative powers just mean flip, right? That's all they mean. The great thing about that is if 2 cubed is 8, 2 to the negative 3 is 1/8. You just flip what you would normally get. That's all you do with negative powers. And so this graph is this. How do I graph the inverse of this?
Flip the.
Yeah, so like, I don't know if this shows up for you guys. This is the point 1, 2, so now it's going to be 2, 1. This is the point 0, 1, so now it's going to be 1, 0. This is the point negative 1, 1/2, so now it's going to be 1/2, negative 1. What happens to my asymptote?
That's horizontal.
So currently it's y equals 0. So of course inverses switch x and y, so now it's going to be x equals 0. So now it becomes vertical. Yeah. Okay, very exciting shit. What I want you to realize is, I know you've probably at some point in your life you've seen this 2 to the x business. You might even have seen e to the x, potentially. I can't remember, I think I talked about it, did I talk about it yesterday? Who was here yesterday? Was I alone? I might have been talking to an empty room.
I don't think you did.
Good. Has anyone ever heard of e to the x? Okay. Has anyone never heard of e to the x? Okay, I love it. You're like, what the shit are you doing, Jeff? What about c to the x? What's wrong with that? All right. E is a number like pi. Not for the same reason, but for analogous reasons. We'll get into e in a minute. So pretty cool with what I just did. There's one function up here that we know the form for. That's 2 to the x. That is the inverse of this function. Did I think at the very end of class I did this. Is this true? Did I give you what this guy's functional, what it looks like? No, okay. So here's the thing. Here's the thing. Let me talk about this directly for a minute. We all know what this symbol means. What do you got, Jeff? What does this symbol mean? Like if I have this, what is it asking me to do? Doing what to it? Square rooting. So what is the answer? 3. So you guys barely have to think about that because you've internalized what that symbol means. That symbol, if you really think about it, it's freaky, but it's not that freaky. It's like this little thing, and if my number is sitting inside of it, I know what to do with it. There's a sentence hidden here. And that, of course, is the idea that math is a foreign language. That symbol, the sentence behind it is, what does it take 2 of to multiply by 9? Of course, math people, we're lazy. I don't want to write that much. And I don't write well. You don't want me to write that much. So we use a symbol, just to mean all of those words. This was probably, I was telling my other class that the day that they came up with this, I think they were all up on the opium. This was a bad choice for notation. They called this, and so do we now, they gave this name. It's a logarithm. Can you guys tell me what's the base of this function? What's the base? 2. So the way I read this is log base 2 of x. Log base 2 of x. When you input a number here, what does it become? That's a weird thing to say. Where do I put the, if I put f of 7, where do I put the 7? In the power. Beautiful. So an input for this function is a power. How do inverses work? Whatever the input of one is becomes the output of the other dude. So the input for this guy is a power. The output for this guy is a power. You guys are all with me? So watch. I'm getting a little bit ahead, but this is fine. If I ask you this question, here's what I'm asking you. This hides a lot, just like the square root of 9 hides a lot. You guys don't even realize you're translating. Has anyone ever learned a foreign language? And if the foreign language you learned was English, I apologize. Because English is like the dumbest language on the earth. Because we just borrowed everything. What did you learn? So when you were first learning Spanish, was it relatively recently or were you?
In high school.
Okay. when you're first learning Spanish and you learn brand new vocabulary word, did you have to stop and kind of like translate it as you were talking? You know what I mean? Yeah. So I'm sure everybody who's ever learned a foreign language, you've experienced this. Square roots are like for the word that all Americans know for sure in Spanish is hola, right? And gracias maybe. We don't even think about it. We know exactly what it means because we're exposed to it all the time. Yes? You with me? And the Spanish-speaking people are like, oh, let it go there, Mr. American. Okay. In math, the same thing happens. You don't even think about the square root. You've been exposed to it for so long, you don't even translate it, you just know what it means. Like, look how fast I'm talking right now. If I started talking in French, because I took a few years of French in high school, forget about it, I would slow down a lot. Yes? Is everybody kind of with me? So this, students hate logarithms because I don't think people tell you the full story. You don't have the question it is asking you internalized. You don't have that. You have to manually remind yourself every time it shows up, just like when you're learning Spanish and they give you a sentence, you got to manually remind yourself, okay, that means this. She went to, you know, that's when we're learning a different language. So what is this asking me? It's asking me, what power does 2 need to become 16? Fourth power. That's it. That's it. That is it. Hey, did you know? That's it. Did you realize? That's it. That's all longs are. It just says, what power does this base need to become the inside number? Why does it make sense? The inputs for exponentials are powers, so the outputs for their inverse functions, logs, must be powers. So, what I want you to do, I went a little far, which is great, because it kind of helped you get ready for this. I'm going to give this out to you guys, and then I want you to work together on it. Someday I'll get everybody to talk to each other. Can you guys, actually, before I put you groups, go ahead and read through it just a bit on your own. So you all go into the groups kind of knowing what the hell's going on. I can't remember, I don't read that. I think you might. And I was going to I like to put little pictures in the corner and put groups together. If you came here after I said this morning, a tree fell in my car. So that's why we're gonna leave a little early because I have to go meet my insurance adjuster person, blah, blah, blah. Yes? I drove my car here, so it's fine. It's just got a big old dent in the front of it and the one headlight just cracked out. So, yes?
How early is a little early?
Huh?
About how early is a little early?
2 at the latest. Yeah, because I gotta go meet them at 2:20, and that should be perfect. So I'm trying to leave a little before 2. We'll see. All right. I'm sure none of you guys are gonna cry, so much on that. So read through that. 2, 4, 6, 8, 10, 12, 14. I love you guys. It's always an odd number. So I can do groups of 3. Yeah, groups of 3. All right, so I'm going to construct your groups for you. Yeah. And we're seeing you guys. Can you guys come over here and you 3 work together? Leon, can you work? You guys work together, and you come up here. You 3 work together. Find somewhere to be together with each other. Can you guys work? Johnny, can you come over here with these guys? Yeah, right here. Okay, just turn around. These guys. What have I got left? I guess you guys. You turn around here with that. You guys almost always end up in a group. Did I get everybody? Four somehow. I don't know how that happened. Call me or Christina over. You need help? Try to do as much as you can of this. So guys, let's take a look here. If like 81 is a little big, so if I give you a bit like a number inside your log that's really big, just start to factor it. Because what are you trying to find? You're trying to find how many 3's multiply to be this thing. So if you break that problem down, so just to show you, I think most of you guys might not have needed to do this, but 81 is 9 times 9, and each 9 is 3 times 3 times 3 times 3. So how many 3's did it take to multiply to the 81? 4. So I mean that's a way to work the problem out. If I give you a bigger number than you wanted, just start cutting it down into size. The question is, how many 3's does it take to multiply this number inside? And every time I say that, I always think about how many licks does it take to get the center of a Tootsie Roll. Is everybody with me? So I don't know if you had to do that, but that's always there for you. Part B is easier. Yes? How many 4's multiply by 16? Or what power? 2. Yes. So how do you check yourself? 4 squared is 16. So over here, 3 to the 4th power is 81. Check. Yes? So you can always rewrite something that's currently logarithmic. You could rewrite it as exponential. This one is either easy as shit or freaks people out. And also you have to remember what this is. What do I raise anything to get 1? 0. Of course, except 0, but we don't talk about that yet. 0 to the 0 is weird. 7 to the 0 power is 1. And we've proven that before, yes.
I was going to say, because I overcomplicated it a lot for myself when I looked at it, but couldn't it also be 1 over 7?
1 over 7, all right. If I put a 1/7 there, that would mean 7 to the 1/7.
Yeah.
And that would just be the 7th root of 7.
Oh, okay.
Which is not the answer I want, right? That's not 1. You guys with me? The 7th root of 7 is the number that I multiply by itself 7 times to get 7. Does such a number exist? Yes. Is it nice to look at? No. Is it 1? No. You guys with me? I need you. Okay. This one is sort of like that one. How many 2's does it take?
4.
4 2's. So 2 to the 4th is 16. You can always rewrite a logarithm as an exponential. Exponentials are more immediately make sense to us. E is a little trippy at first, maybe. E is also, once you see it, it's kind of dumb. So here's what it's asking. It's asking this, literally. What power do you put on B to make it become B to the 8th? You put a power of 8 on the damn thing. Another way to look at this. Does everybody see that? I think I see that. I like to give freaky ass problems like what's log base pi of pi to the 11th power? What would that be?
11.
11. So another way to look at this, remind me, how does 2 to the x relate to log base 2 of x? What's the relationship between those functions? I have 2 to the x. How did we create log base 2 of x? What is that in relation to 2 to the x? What kind of functions are they? Inverse functions. What do inverse functions do to each other if you plug one into the other one? No, that's how to find an inverse. What do they do to each other if you put one into the other one? They kill each other. Just to show you, what's the inverse of cube rooting something? What's the inverse of cube rooting something? You can do it. What's the opposite of cube rooting something?
The exponent of 1, or
Cubing it, yes? What do these do to each other? Yeah, so inverse functions, what do they do? What's the opposite of adding one? So if I have x plus 1 minus 1, the two functions kill each other and you have x left, yes? So watch this. Log base b and b to a power are opposite functions. They kill each other. What's the only thing left? 8. That was the answer. Log base pi and pi to a power are opposites. 11 is the answer. Yes? Do you guys see that? So let me immediately show you another kind of problem. What would this be? W. 3 to a power and log base 3. What kind of functions are they? Inverses. What do they do to each other? Kill each other. Done. Okay, maybe. Now, of course, for a lot of us, logarithms we just talked about them. We just came up with them. So you're not used to them yet. I don't blame you. I'm almost certain most of you guys have seen logs somewhere before, but some of you might have blacked it out of your memory. I don't know. A lot of students hate them for some reason, and I don't blame too much. I was showing one group, if I didn't have the one there, if it was just log base 5 of 5, what would the answer be? Just log base 5 of 5. It would just be 1. And then how do I flip something and make the power negative? So what's log base 3 of 9? No, how many 3's make 9? 2. And then how do I flip it? Make the power negative. Do you guys see that? So if I log of a fraction, I could just kind of make the bottom happen and then make it negative. Yes? Yes, sir.
What if we had a more complex fraction, like if g was 2 over 9 instead of 1?
Oh, okay. Obviously, these are exploring the idea of logarithms with numbers that work nicely. Just like we do with square roots. When we introduce the idea of square roots, do we immediately go to the square root of 71? Do we do that, or do we start with the square root of 81? Why do we start with the square root of 81? Because it's nice. But even more than that is so I can explore the idea of the square root. Once we get the idea of the square root down, we start to say, can I do anything with this dumb thing? You with me? So for example, square root of 81 is? Holy shit. What's the square root of 20? Do you know what the square root of 20 is? I could estimate it, but I don't know what it is. Like almost 5, yes. So if I had to really guess, I'd say 4.7. If somebody was telling me they're going to kill me if I don't guess. You guys with me? That happens often. You don't know. Can I do anything with rad 20 though? Can I still do something with it? Because now, once we do simple examples, we can build on that. You guys with me? And then we can talk about the ones that we actually can't do shit with. Because not even this method, this is 4 times 5, yes? I can't do shit with 71. So this would be square root of 4 times square root of 5, which is 2 rad 5. I can at least reduce it. But I could never get here if I didn't start with this, yes? So right now, we're at the level of just exploring the idea. But just to show you, if I had like paper, it'd be amazing. Oh, there we go. If I had like log here, let's take the next level up. I'm going to change the one I gave you guys a little bit. Log base 16 of 8. Don't those numbers feel like they should go together? But when I'm talking about powers, they don't go together too well, do they? Okay. So this is in the direction of your question, because your question is sort of like the square root of 71. We couldn't do too much with it, but there's a little bit we could do once we learn more about logarithms. I can reduce that, sort of like we reduced the square root of 20, but we're not there yet, yes? This is the first problem I've shown you that you can't just go, well, yeah, that's 3 or something, right? It's not negative, you with me? Because is it fractional?
Yeah.
Is this fraction? No. So it's not a negative answer, right? I don't flip something. You with me? Logarithm's all about exponents. So I don't care that 8 is half of 16. It's not multiplicatively half of 16. So that the fact it's half doesn't mean shit. I don't talk about additive stuff with logarithms. I have to talk about multiplicative stuff. So I'm going to stop. We're going to actually do this problem. You're like, great, Jeff. How do we do the damn thing? Does anyone know what the answer is? Okay, what do we call it if we don't know what it is? In algebra, what do we call it if we don't know what it is? X. Undefined is if we know that it can't be defined. Okay. And what did I say earlier? How do I rewrite this as an exponential?
16 to the 5 equals 8.
Good. You can always do this kind of like, what? Last semester, my 171 students call it the washing machine. I love it. It's the washing machine, yes? 16 to the x equals 8. 16 to the x equals 8. And you guys are like, right now, I'm sure you guys are like, okay, thank you, Jeff. That's so much better. Can you guys tell me, is there a number that 16 and 8 are based on through powers? Because logs are all about powers. 2. They're both based on a base of 2, yes? Stay with me now. Stay with me. Is everybody with me? We've kind of taken a little bit of a step here, but I'm going to show you this algebraically, and then I'm going to show you a shortcut, and then we're probably going to leave after that. So 16 is 2 to the, we just did this, 4th, and 8 is 2 to the 3rd. Now listen, what's the only, one more thing. What can I do with these powers? Does anyone remember? When I have something with the power raised to a power, what do I do with the powers? No. You multiply. Why do I multiply? Because what does this mean? 4 groups of 2 x's. Okay, what's 4 groups of 2 x's? How many x's if I have 4 groups of 2?
16.
Okay, I got 4. One group has 2. And I have 4 groups of 2. 8. That's the definition of multiplication, yes? 4 boxes, each box has 2 apples in it. How many apples do I have? 4 times 2. Yes? All right. So when I have something with a power raised to a power, I multiply the power. So what is this? 2 to the? Don't overthink it. Huh? 4x. What is the only way 2 to the 4x could equal 2 to the 3? What has to be true in order for that to work? Well, this would have to equal this, yes? Do you guys see that? The bases are already the same. In order for them to be fully the same, this has to equal that. And then how do I solve for x?
Define 3.
Okay, now, dear God, you can sink your teeth into this. This is stuff you could do. This is algebraic manipulation that you could do. I'm going to show you a shortcut that kicks. I say this a lot. I don't care. It kicks a lot of ass. This is so cool. From the beginning. If I break 16 all the way down, what is it? 2 times 2 times 2 times 2, yes? If I break 8 down, what is it? 2 times 2 times 2. So, what is 16 made up of? 4 2's. What fractional part of this is 8? What's 8 made up of? 3 2's. So how much of this? All 4 of them make 16. How many of these do I take to make 8? How many of these make 8? 3 out of 4. 3 out of 4. 3 freaking fourths. Yes? If I take 3/4 of what makes 16, I make 8. That's another way to get the answer of 3/4. I'm not going to require you to do it that way because it's kind of trippy, but I do like to show you the shortcut because it kicks a lot of ass. And I lied a little bit. One more. What about this one here? What is log base 8 of 8? Log base 8 of 8. What power does 8 need to become 8? 1. What's log base 8 of 1?
1.
No, let me write it. Log base 8 of 8 is 1 because 8 to the first power is 8. What's log base 8 of 1? What power does 8 need to become 1? 8 to what power is 1? 0. Do you see how this answer must be between, what is that, Jeff? 1 and 0? Because the input's between 1 and 8. Do you guys see that? So I know the answer is going to be fractional. What do fractional powers represent? What's a 1/2 power? A 1/3 power? What do they represent? Roots. A 1/2 power is a square root. 1/3 power is a cube root. Yes? So what root of 8 becomes 2? 1/3. Done. Done. So if you don't have to memorize this, but if I have an input that's between the base and 1, the answer is going to be some kind of fraction because it's got to be rooted. It's got to be cube rooted or 4th root or something. You guys kind of with me? Now listen, we're just starting to get into this. And I kind of get into these harder problems maybe a little too fast. I just want you to accept that logs are really not that hard. If you remember their powers, you have all these brute force methods of figuring out the answer. You're like, what power does this need to become that? That's the way you attack a question. Yes? All right. That's enough. That's enough. I'm going to go find out if they'll cover my stuff. Thanks, guys. I will see you next week. Wednesday, of course, we have the next quiz.